morning. Welcome to this course Foundation Engineering, and we are almost towards the end of this lecture series. And the last topic I was discussing about machine foundation, and that too introductory, not much in detail. And I have discussed already forced vibration, free vibration, damped, undamped, all those things. Now, we have to think about the foundation design, and foundation design means normally when we design for a foundation for a building or any other thing, then basically our criteria will be bearing capacity and settlement. That means, because of the building loading, whatever pressure coming to the soil should be less than the bearing capacity to the soil, and also because of the loading whatever the total settlement it is causing, that should be within the given limit. So, these two criteria generally used in normal regular foundation for static loading, and when it is a dynamic loading, as I have told already at the beginning, that it is a natural frequency and the amplitude, resonant amplitude. Resonant amplitude actually see amplitude, mainly actually is amplitude, and that amplitude, the vibration amplitude should be within some limit. And we have investigated for different types of forcing system, whether it is a constant force system or the rotating mass system, and with the variation of frequency how amplitude varies, that we have seen, and we have shown that the amplitude is very high, close to the resonance frequency at resonance. So, because of that, in the design actually basic guidelines actually that you have to design the machine foundation in such a way that its natural frequency should be far away from the operating frequency of the machine. So, that is one thing, because if the operating frequency is much lesser or much higher than the resonant frequency, and there actually amplitude is generally less, very less, whereas it close to the resonance, it is a very high, significantly high. And so, because of that we need to restrict the amplitude by designing the foundation in such a way that its natural frequency should be away from the operating frequency. This is the things, and based on using the based on these guidelines, if you want to design, then what are the different types of machine for foundation for different types of machine. So, that actually we have some guideline. You can see there are, this can be classified into 3-4 categories. You can see one actually foundation for impact producing machine. So, that is one type of machine. That means, suppose there is a hammer foundation, suddenly a weight will fall, and to fabricate something, and because of this heavy weight falling on the some object, it will create some vibration, and then for that type of foundation, that type of vibrating system, you have to have different foundation than other type of vibrating system. So, that is what you have classified one, that is foundation for impact producing machine, that is like hammer, press and all. Similarly, another is foundation for machine producing periodical forces. That means, periodical forces means, that means you have suppose if the machine contains a eccentric rotating part, that I have told a number of times, that if you have the eccentric mass is rotating with respect to the center, and because of this operational frequency, this force will be here m into E into omega square. So, this is the force. So, that means, if that type of force is there, and then there will be, that means the foundation for machine producing periodical forces, that means this type of force is actually same force is repeating and some interval, that is actually periodic force. So, this also will create periodic force, and so foundation for machine producing periodical force, that for that also there is a different types of foundation. Similarly, the foundations for high speed machineries, again periodical force can be of moderate and it can be medium, it can be high. So, if it is a high frequency, there is a typical type of foundation we use, and so that is what another classification can be done, that foundation for high speed machineries, and then miscellaneous, that means different other kind of any machine. So, it requires some foundation. So, depending upon type of force and of frequency, one can decide the what type of foundation is required. So, now these are the classification. Now, what is the guideline actually? Guideline is when it is a machine producing impact or impulse, machine produce impulse, generally suggested foundation block type foundation. Block means it will be a suppose something like this. A block like this of length, width and height, or if it is a circular, it can be something like this. Okay. And in over that impulse force will be applied, over that impulse force will be there. So, machine producing impulse, that means if there is an impact type of machine, then suggested foundation generally is block type foundation, and example of impact producing or impulsive force will be hammer and press and similar kind of things. Then next is rotating type machine with low to medium frequency. This is actually low to medium, assume low frequency, and suggested foundation is block type foundation with large contact area. Okay. So, why it is so? When the operating frequency is low, suppose say 200, operating frequency is low, 200 RPM. In that case, actually we generally design overtune. Overtune means natural frequency high. So, natural frequency if you want to make high, then what you have to do actually, natural frequency is actually under root k by m, that means k by m, to make k by m high. So, it is easy, you can easily increase the k by increasing the area, because k equal to 4 g r by 1 minus mu. So, this is r. So, radius actually see, that means that is why rotating type machine with low to medium frequency suggested foundation is block type with large contact area. Why large contact area? When contact area becoming large, then k become large, and when k become large, then natural frequency becoming large, and that is the purpose. That is because low frequency machine we generally give design for overtune foundation, and overtune means natural frequency should be higher than the operating frequency. So, that is why this is the one type of guideline, that low to medium frequency foundation machine suggested foundation will block with large contact area. What is the reason for giving large area? Because you want to increase the k. How to increase the k? By increasing r, and if you increase k, then what is increasing? It is increasing natural frequency. So, that is the way we decide that. And what are the example for this low frequency machine? They are actually large reciprocating engine, compressor, large blower, they are coming under this category, that means low frequency machine. And if this is the type of machine, then we have to go for block foundation with large contact area. That means the base area will be more than the height. Next one. And then next one is again the rotating type machine with medium to high frequency. So, in that suggested foundation block type foundation resting on suitable pad or spring. That means, if there is a high frequency machine, then there is a chance of vibration, large vibration amplitude. Because of that, one can have below the block this is the block foundation, one can keep some spring or some absorber, and then it can be constructed. So, that will help actually to reduce the amplitude. So, if it is a rotating type machine with medium to high frequency, then it will be again block with some absorber below it. Okay. And example under this category will be medium size reciprocating engine, then diesel engine and gas engine. So, these are the kind of machines for which actually you have to go for block foundation with suitable elastic pad or absorber. Okay. And then third category actually rotating type with very high frequency, and when it is a very high frequency as I have mentioned already. So, high frequency suppose 3000 rpm, and then if the operating frequency is 3000 rpm, then your natural frequency will be less than that, that means it will be this side. So, it will be maybe suppose 1500 or 1000 something like that. So, this is called under tune. That means, when there is a high frequency machine, for that when you want to find out design for foundation, then you have to design for under tune. Under tune means what? Whatever natural frequency or whatever operating frequency is there, you have to design in such a way that its natural frequency falls below that. That means, it will be half or even lesser than that. So, this is under tune design, and if you do that. So, because of that you can see for high frequency machine, the suggested foundation is actually generally frame foundation or massive block with minimum contact area. So, generally frame foundation will be there. If it is a frame foundation, then it will have lesser stiffness, and lesser stiffness means it will have your under root k by m. Under root k by m, if stiffness is less, then automatically omega n also will be less. So, that is the purpose, and sometime huge block can be also used. In that case, the contact area should be less. If you use block and contact area, why should be less? Because your k become 4 g r by 1 minus mu. If you reduce the r, then k will be reduced, and if you reduce the k, then omega n also will be reduced. The way actually for low frequency machine, we made large contact area to increase the k, whereas in the high frequency machine we reduce the area to reduce the k, and so that your natural frequency will become less. So, high frequency machine generally under tune, and to do under tune generally the frame foundation is suitable, and if you use the block foundation, then the block contact area should be like that. Means, its block may be something like this, a huge block actually smaller contact area, but height will be significantly high. So, it may be like that, whereas if it is your low frequency machine, block area may be dimension may be big, but height may be the area will be this, and there may be height will be something like this. Okay. So, these are the different guidelines. If you know the type of machine, then you can adopt accordingly, whether it is a block with small contact area, block with large contact area, or frame foundation, or you can have the block foundation with some absorber. So, based on frequency range, we can decide that. And these are actually some example are shown here, actually a photograph of typical block foundation. If it is a block foundation, this is the block, actually this is the entire mass actually by concrete and block, and it will be fixed. This is suppose machine is fixed onto the block, and because of this vibration caused by this machine, it will be passed through this foundation to the ground, and that is the typical design. Some more detail will be there, but we are not going much detail about the connection etc., which is there in the code. And another block can suppose one can think of to reduce the mass sometime, to make it increase the area, but mass can be kept less. So, in that case actually it can be made hollow block. That means, we can make a block with some hollow portion, So, that is also another type of block foundation can be used sometime, because you have to adjust natural frequency. Sometimes you have to natural frequency reduce it, sometimes you natural frequency increase it. So, by doing this, what you can do, under root k by m, area increase. So, k is increase and mass is reduced. Of course, this has to be optimized. So, if mass is reduced, then natural frequency will be increased. So, some adjustment has to be done by doing this process. And this is actually typical frame foundation. You can see this is the front view actually, and this is a cross section. Suppose if you cut like this is a machine and this is the frame, and this is the frame, and there will be this is the frame actually. On the frame, at top of the frame there will be deck slab, and at the bottom there will be bottom slab, and bottom slab will be make a very thick. Generally it will so thick that while analyzing this frame foundation, we assume this frame are fixed at this level. So, soil information will be ignored here, and then according to this position of the loading etc., some vibration analysis has to be done, but the frame foundation analysis we are not going, because it is a detailed machine foundation class only. You can do it here, only just introductory only I have given. So, only what type of foundation when the frequency is high, that only just to show that only I am bringing this foundation type here, but not detailed design. And this is actually a typical hammer foundation. You can see here there will be arrangement, and this is the frame, and this is the anvil, and then by lifting this, the load will be falling on this anvil, and you can see this will be main foundation, then elastic pad, then there will be anvil, and then there will be this arrangement through which the load will be lifted and allowed to fall, and on this impact will be producing on this anvil only. And when this type of foundation is there, simple way, the way we have done analysis, that is actually a single degree of freedom. That means, we have a mass, and then we have a spring, and we have like this, or additionally we may, when it is a damped, then there will be dashpot we have done like this. This is a single degree of freedom, but here actually you can see foundation here, this layer will act as one spring, and again the soil also will act one spring. This is one foundation, that mass, this will act another spring, and this is another mass. So, this type of foundation will be designed or analyzed like a 2 degrees of freedom, that means one spring, then another mass, then another spring. So, this spring actually representing soil, this actually between foundation and anvil. So, this layer. So, this is actually corresponding to this layer, and this soil corresponding to this one, and this mass corresponding to this concrete, and this mass corresponding to this anvil. Okay. So, like that 2 degrees of freedom has to be done for this type of foundation, but we have not done 2 degrees of freedom. We can again similar to that, if I write k 1 and this is k 2 and it is m 1 and m 2, we can write down the equation of motion, and you can also solve for it. So, that part of course, out of the scope of this class. So, I am not bringing that, only I am just mentioning that how hammer foundation look like. This is generally it will be like that, there will be the job will be performed on this anvil, which is a okay. And so, like shoemaker, they have anvil similar to that here, that the object will be here, and then by some arrangement that it will give you proper shape, and for that the heavy impact will be produced on this anvil to it will go to the foundation through this spring. So, that analysis of course, I am not doing here. Now, typically I have discussed vibration theory and all. Typically machine foundation, how we have shown only like this, one mass and one spring, and if necessary sometime we have given one dashpot, something like that we have done. But how it will be related to the foundation resting on the soil. So, that is what actually if you see here, this is a suppose this is a foundation resting on ground, and on the foundation this suppose machine, and this machine suppose producing something f naught constant and force equal m naught sin omega t, or similar to that there may this is also foundation, this is soil, and on that there is a machine which is producing f equal to m naught sin omega, where f naught equal to m into E into omega square. So, two different types of forcing system are shown here, and whether it is this or this, typically I can idealize that machine and foundation together, this is as a mass machine and foundation, and this soil will be represented by a spring and a dashpot. And if it is done, then and this force either it can be this or it can be this, and this is the model actually we have taken right from beginning, and from this model how to find out the equation of motion. That equation of motion will be this, and f t can be either this or it can f t can be this. So, because of this f t equal to this or f t equal to this, solution for this equation already we have done, and we have observed with the variation of frequency, what is the variation of amplitude at different frequencies, that we have observed. So, same thing only I am now correlating with the foundation. Before that what we have done, I have assumed a mass on the resting on spring, and for that I have done analysis. Then how it has to be connected to the machine foundation on soil. So, that actually you can see that this foundation resting on the soil, then that entire foundation soil will be replaced by a spring. Okay. So, that means that springs, that means to analyze machine foundation we need to find out the spring coefficient k, and for that we have mentioned that if it is a vertical vibration, your spring coefficient will be 4 g r by 1 minus mu, where g is the shear modulus, and how to determine shear modulus we have discussed. R is the radius of the foundation and mu is the Poisson ratio. But here actually you can see we are mentioning only R circular, that means radius of the circular foundation. That means this theory cannot be applied if the foundation shape is rectangular or square. It is not so. Actually it can be applied. How we can apply? If the contact area of the foundation is something like this, suppose this is A and this is B, then your area is actually A B, and we can find out equivalent area by equating this. That means, I can find if there is a rectangular foundation, I can find out equivalent radius equal to under root A B by pi. Okay. So, this way, so if it is a circular foundation, definitely directly I will take use R and use this equation to find out the k, and if it is a non-circular, then I can find out R by equivalent method and then use that and find out the k. That is one thing we need to find. That means, when you replace the soil by a spring, and that spring stiffness has to be obtained, and that actually 4 g r by 1 minus mu, it has come from the elastic theory. That means, if I apply load here, then what will be the amount of settlement, then finally load divided by settlement, if I do elastic settlement, if I do, then this expression comes when it is a infinitely homogeneous soil is there. So, that is one thing to be obtained, and then next thing k, then the second thing is actually C, that is damping coefficient, and damping coefficient actually is difficult to do. Damping again can be of different types of damping, particularly in machine foundation vibration. There is another type of vibration is there, damping is there, that is called radiation damping, which we will not discuss. For the time being, we can think of only the material damping, and that material damping actually for it depends on the material type. Different material will have different material damping, and it vary actually some 1 or 2% to 10% material damping. So, that I will show you in the next slide. So, that means k to be determined, and then C, and of course, if you know this, then of course, you need to know the mass. Mass actually here mass of the foundation plus meshing, that to be used as a mass, though there is some amount of mass will vibrate along with the foundation, but generally it can be ignored. Mass means it is a mass of foundation plus meshing. So, if you know all those parameters, then we can solution for this equation is given, you can find out amplitude, you can find out natural frequency and all those things without much difficulty. Now, as I have told you that your damping, different material will have different damping. You can see that is a report is given here, how the range of damping dry, sand and gravel, the material damping range between 3 to 7%, and it is given by this person. Dry and saturated sand, the material damping can vary between 1 to 3%, that is given by him, and dry sand, that you will have material damping ranging actually up to maximum 0.3%, it is given on Whitman. Dry and saturated sand and gravel, the damping vary between 5 to 6%, it is given by Barkan. Okay, and the clay, the damping vary between 2 to 5%, that is given by Barkan again. Silty sand damping vary between 3 to 10%, it is given by Stephen. Dry sand damping given 1 to 3%, that is given by Harding. So, that means, if I look at this, so approximately 0.2% to 10% damping can be assumed. If damping is not given for the analysis, what I have told you that you need to know the mass, which is equal to mass of the foundation plus machine. Then you need to know the stiffness, that means which is equal to 4 g r by 1 minus mu, that is actually for circular foundation. If it is non circular foundation, r can be obtained by equivalent circular area, that means under root a b by pi, and then you need to find out damping, and damping value if it is not given, then we can find out something in the range of 2 to 5, approximately 5% if you approximately 0.5 if you assume that most of the time it will be useful. So, and in fact, in machine foundation vibration another kind of damping is there, which will be much more than this and which should be considered, but we are not discussing right now, because that is required some more information. So, I am not going in that detail. Next thing actually, if you look at the response, that means, if you find out amplitude versus omega over omega n, and you will see that when the we can approximately find out the resonance frequency, approximate estimate resonance frequency, if you know the k and m, though resonance frequency is little bit little more or little high depending upon your forcing system, whether it is a constant force system or rotating mass system. So, we have seen that once resonance is if this is the omega over omega n equal to 1, some responses are coming like this. Okay. So, it is changing like this, and for constant force system resonance occurring before 1, actually frequency ratio 1. So, that is what resonance frequency slightly away from the natural frequency, sometime little more or little less, but if you want to find out approximately natural frequency, simply you know the k and m, then you find out under root k by m, that become the approximate natural frequency generally you will get, though resonant frequency your resonant frequency can be taken as natural frequency when damping is small, and if it damping is large, I have given relationship that can be used to find out correctly what is the resonant frequency. Similarly, if you want to find out approximate amplitude and two frequency range, if the operating frequency is very small, then k is important, because you have seen that at a very low frequency that the amplitude, whether damping is there or not, almost same, all the curves are very close. So, because of that approximate estimate of motion, actually when the frequency is very small, k is most important, and when actually frequency is very large, then actually for finding out the motion or calculate the motion, m is important. The mass is more, then a large frequency amplitude will be reduced actually. That is why it is important. So, when large frequency machine, the mass should be more, that is the guideline actually. And if the upper limit of motion at frequency near resonant frequency, actually when at resonant frequency you see that damping is the most important. If you put 0 damping, it is theoretically infinite. If you put 1% damping, then significantly it will be reduced, it will become finite value. If you become 2%, 5%, 10%, and then it will be reduced. So, near resonance damping is most important, and otherwise for some time, and k and m also important, because of depending upon whether it is a constant force system or rotating mass system. So, these are the observation actually from the if you know the frequency versus amplitude, that plot if you see, these are the observation can be made and which can be used as a guideline for the design of machine foundation. So, with this I will stop here. Thank you.